So let's see some examples of finding area using a double integration. So we'll find the area enclosed by the curves x equals y minus y squared. So that's this curve, and y equals negative x, which is this. So as a first step, we'll find the points of intersection. So y equals negative x tells us that that x is equal to negative y. And so then we can set this and this equal to each other. So negative y equals y minus y squared implies that 2y minus y squared equals 0. So y is equal to 0 or 2. So the points of intersection will be something comma 0, something comma 2, and from x equals negative y, these points will be 0, 0, and negative 2, 2. Okay, so now let's try to find the area using that. So first of all, there's sort of two distinct parts to this region. So we'll break it up as this one to the left of the origin. We'll call R1, and that's where the line 1 minus x is sort of the bound below. And in the second one, which region we'll call R2, it's entirely the quadratic function x equals y minus y squared, which is defining the bounds. So we found these points of intersection. Okay, so if x is equal to y minus y squared, then we can solve for y as a function of x using the quadratic formula. We get y equals 1 plus or minus 1 minus 4x all over 2. So the integral, the area of R1, this is going to be, so we're integrating with respect to y first, since we have vertical slices, then with respect to x. Our x value from this goes from negative 2 to 0, and then our y value goes from 1 minus x to 1 plus square root 1 minus 4x all over 2. And here we take the positive. We take the positive sign. In the negative sign is below the x-axis, and it's not what we're interested in. Where we see the other, the negative sign comes in, is to calculate the area of R2. So that will be integral. Well, we need to find the coordinates of the base of this parabola So from this this formula, that will be when the square root is equal to 0 is when we get the apex of the parabola. So that'll give us 1 minus 4x is equal to 0, gives x equals 1/4, and then y is equal to 1/2. So the integral for d2 or sorry, for the area of region R2, R2 dA is integral. Now x is going from, so we're still doing dy dx is the order of integration. Now we're going from 0 to 1/4 for the value of x. And now the y value is going from here where we take the negative square root and here where we take the positive square root. So this is our integral. This looks pretty complicated. So let's try doing it the other way. Okay, so if we do with horizontal slices, then first of all, we don't need to break the region up into two pieces. So integral of r dA. Now we're going to be doing the dx x direction first and the y direction later. From our bounds, we know that y goes from 0 to 2, and then x, so our equations are, x will be going from 1 minus y, or sorry, minus y to y minus y squared. And now this we can evaluate much more easily. So this is integral from 0 to 2 of y minus y squared. So 2y minus y squared dy. And so that's y squared minus y cubed over 3, evaluate at 2, and then 0. So that's, let's see, 4 minus 8 over 3 is 12 minus 8 over 3, so is 4 over 3. Next, let's try finding the area of the region where it's given by y equals 2, y equals 1 minus x, and y equals e to the x. So that's what this looks like. So first, let's try doing this with vertical slices. Well, again, we'll want to break up this integral into two different regions if we're doing it this way. So R1, which is where 1 minus x is the bottom bound, and R2, which is where e to the x is the bottom bound. So that'll give so if we do that, we'll have well, the area of R1. This, just from simple geometry, we could see is 1/2 from area of a triangle. So then the integral, the area of R2 on the other hand, this will be, so we're doing it vertical slices first. Well, if y is going up to 2, so y equals 2 and y equals e to the x, means that our boundary for x has to be ln of 2. And since from where we've started R2, our bottom bound for x will be 0. And then the bounds for y are 2 and e to the x. So we can evaluate this. So this will be integral from 0 to ln of 2, 2 minus e to the x dx, which is 2x minus e to the x at ln of 2 and at 0. So that is 2 ln 2 minus 1 overall. And then remember we also had this term. So the area of dA for the entire region will be 2 ln 2 minus 1/2. Now let's also do the calculation with horizontal slices. So y equals 1 minus x turns into x equals 1 minus y. And again, y equals e to the x turns into x equals ln of y. So now, and we don't need to split this into two regions. Now we can just do sort of integrating dx dy. So y we can see will be going from 1 to 2, and x will be going from, so the lower bound is 1 minus y, the upper bound is ln of y. So this is integral from 1 to 2 of ln y plus y minus 1 dy, and integral of that will be y ln y minus y. So this is the integral of ln of y plus y squared over 2 minus y, and then this all evaluated at 2 and at 1. So that works out to 2 ln 2 minus 2 plus, this is terrible, isn't it? Plus 4 over 2 minus 2, and then minus 1 ln of 0, so minus 0, plus 1 minus 1/2 plus 1. So these cancel out, and again, we're left with 2 ln of 2 minus 1/2 is the area.